The heat engine with the highest efficiency is the one that I've drawn right here. This is called the Carnot cycle, or the Carnot engine, after the French physicist Sadi Carnot, who lived in the first half of the 19th century and is one of the founders of the modern field of thermodynamics. So, why is this the most efficient engine that we could ever conceive of? And the answer is a bit elusive. I'm actually going to release a supplemental video where I explain the theorem called Carnot's theorem in more detail that shows that this is, in fact, the most efficient heat engine. But we should at least try to get some handle on what's going on here. All right, so first of all, just what is this engine? What are the four strokes that I've depicted here? Well, I've numbered them 1, 2, 3, and 4, and they go as follows. Stroke 1 is an isotherm. So that means it's at constant temperature. Stroke 2 is an adiabat. And that means that entropy doesn't change over it, or that no heat flows into or out of the system during this operation. Stroke 3 is another isotherm. And stroke 4 is another adiabat. Notice that stroke 1 is carried out at a low temperature relative to stroke 3, which is carried out at a higher temperature. All right, good. So we have used PV space for a lot of what we've done so far. And that made sense with the kind of stuff that we were doing where we were trying to calculate work. The issue now is that we'd like to know some things about heat, and this is maybe not the optimal space to do that. Notice that in this space for both curves 2 and 4, V as a function of P is something like P to the minus 3/5. Not super nice to work with. So we're going to use some of the powerful machinery from differential geometry that we've shown so far in order to make this a little easier to work with. What we want to do is find a coordinate system where we can more easily compute heat. Remember that heat is the line integral of T ds. And so it sort of just seems sensible to try to work in TSN coordinates, or maybe more precisely, STN coordinates. Let's get those up. Okay, now we actually don't need to do very much work at all to get the basic picture of what this cycle is going to look like in ST space. Notice that curve 3 is all at one temperature, and curve 1 is also all at one temperature. Moreover, because curves 2 and 4 are adiabats, entropy doesn't change on them. And those two facts mean that the only shape that this could be is a rectangle. So this is at temperature TH, and this is at temperature TC. Now it does remain to be shown that, in fact, this rectangle goes in one direction or the other. And we could do it in a number of ways. We would need to figure out what the entropy is at the various points here in order to see which way we should go. But in fact, in the next video, we're going to figure out an easy way to figure out the work done in a cycle, and similarly to figure out the heat done in a cycle. And when we get there, it will actually be pretty easy to show that when we do this change of coordinates in this order, this cycle, which was counterclockwise in this picture, becomes clockwise in this picture. So keep an eye out for that in the next video. Oh, and I said the right thing and then wrote the wrong thing. This should be clockwise in this picture. Okay, now that we have a very poorly done drawing here, we're ready to figure out the heat that's done in each of our 4 strokes. So again, let's number these 1, 2, 3, and 4. Okay, Q1 is equal to the integral over curve 1 of T ds. Notice though that curve 1 is an isotherm, so T is constant, and that constant's value is Tc. And then we just get the integral over ds, but this is a horizontal line in ds. So it's pretty easy to see that what we'll get is S final, which is, let's say, S naught, minus S initial, which is S. In fact, in this case, let's just write minus Tc delta S, where we're not too concerned about what this distance delta S is. Next up, Q2, well, that's the heat change, or the heat that goes into the system, let's say, on an adiabat. But we know that for an adiabat, by definition, that is 0. Good. The other way to see this would be to try to do this line integral. Notice that it's an integral where the variable of integration is s, but that s doesn't change. Kind of the same thing. Next up, Q3 has basically the exact same calculation logic as Q1, but notice that because the curve is going in the opposite direction, we'll get a plus sign. So we get plus TH, since we're at the hotter temperature isotherm, delta S. And lastly, by the exact same logic as Q2, Q4 is equal to 0. Now we ask ourselves, what is QH? Again, defined to be the sum of the heat for all strokes where the heat into the system is positive. In this case, that's only one stroke, 3. So QH here is just TH delta S. On the other hand, what is the work done as we go all the way around? Now, there are a variety of ways that we could do this, but I think just for calculation practice, let's do it in our new coordinate system. Okay, so now what is the work done as we go around this cycle? Now, there are a few ways that we could do this. One of them is to go back to this diagram. Because these diagrams communicate the exact same information, we can use either one of them to compute whatever quantity we want. So we could compute work back in this coordinate system. We're taking these p or minus pdv integrals would be simpler. On the other hand, we could simply use this coordinate system and convert all quantities as we go. I'm actually going to do neither of these and use the technique that I'll introduce in the next video to just produce the answer. So I'm not going to show my work here, but we will practice this later on. So what we'll get is that W is equal to minus TH minus TC times delta S. Putting this all together, we get that eta, which is equal to minus W over QH, is equal to, well, this minus sign goes away. We'll just get TH minus TC over TH. Or maybe written in a more approachable way, 1 minus TC over TH. So now let's answer a question. In what sense is this the most efficient engine? It actually still depends on some parameters of the system, namely Tc and Th. The answer is this. For any system whose minimum temperature as it goes around the cycle is Tc and whose maximum temperature as it goes around the cycle is Th, this is the most efficient engine. Notice in particular that it doesn't depend on anything like a compression ratio. So there are a variety of ways that we could form ratios out of the various combinations of different volumes here, and this doesn't depend on any of those. Instead, it simply depends on this ratio of temperatures. So in a supplement, again, I will go over exactly why this is true. But you should check that for a couple of simple examples, this does work out. Now I'm going to throw back up on the screen the plot of the efficiency of that three-stroke engine from the last video as a function of phi. So we can pretty clearly see from what's up on screen that this engine is always going to be less efficient than this engine. And with that, I think we've basically completed what I wanted to talk about in terms of efficiency of various engines. In the next video, we'll learn a very powerful technique for computing work and heat uh, in the process of these engines. Thanks so much for watching, and I'll see you in the next one.